A black hole has been thought of as a massive enclosure of almost infinite density in its core, surrounded by a more or less rarefied space out to an elevation the event horizon, where even light cannot escape. But conventional black hole theory is not entirely consistent with relativity theory, and I know that's often an overenthusiastic and/or mistaken claim made about relativity and theoretical physics in general, and it's usually focused on a belief that relativity theory is somehow wrong. But what I want to do here is defend and clarify some pertinent aspects of relativity to demonstrate how a more careful, truly relativistic interpretation of black holes leads to an interesting conclusion. Except for, possibly, a finite and residual core of mass, nothing but light can exist within a black hole. This will primarily be a matter of clarifying what happens at the event horizon, at the Schwarzschild radius of a black hole, the elevation where gravity is so powerful that nothing can escape. It's also about more carefully distinguishing what happens to a body that is falling into a black hole from what happens from the perspective of a remote observer. Consider an example: the fate of an astronaut falling toward a black hole. She will be very aware of rapidly accelerating toward the hole. There will be an alarming, expanding horizon of blackness below, which is banded by an accretion disk of infalling mass and energy along its equator. But she won't experience the effects of force in her free fall, just a tidal stretching of her body as the horizon draws near. The tidal effect occurs because gravity becomes significantly stronger at her feet, if she's falling feet first, than it is at her head. So what will the observer see? It's a well-confirmed prediction of relativity that the deeper a body is in a gravitational field, the slower will be its processes, its clock speed, compared to others at higher elevations. This isn't a relative difference, as when two bodies are in uniform motion, and each will observe the other's clock to be moving more slowly than their own. I've described this only apparently absurd situation at some length in another presentation on relativity in a YouTube video linked below the screen. With the gravitational relationship, it is different than with relative motion. Observers at different elevations can agree, and they will be correct, that it isn't a purely relative relationship. It is actual. We could say it is respective, not relative. The clock speed at a lower elevation is absolutely slower, and at a higher elevation, it is absolutely moving more rapidly. Not by much in ordinary circumstances, but the GPS system actually depends on and confirms this relationship. There are several things worth mentioning here about gravitation in general. One entails what few theorists have addressed explicitly. Einstein did allude to it just in passing on at least one occasion, that the speed of light is not actually a constant. Imagine that you're in a geostatic orbit, remaining directly above a location on the surface of the Earth, looking down on a colleague who is measuring the speed of light between his experimental apparatus and a mirror. Not only his clock, but also the light ray itself will necessarily appear correspondingly slower than it is at your elevation. So actually, the speed of light varies with the elevation in a gravitational field. We should say that light is a respective constant. It is only truly constant at the same elevation as an observer. Another point is noteworthy. It is sometimes said that as someone is falling into a black hole, with her clock moving more slowly as seen from above, she could turn around and see the rest of the universe moving rapidly into the future. But that is incorrect. The situation is analogous to the famous twin paradox, and you can also see a link to my treatment of that down below. If she could succeed in turning her fall around before it's too late to rejoin the distant observer far from the black hole, they could have a reunion in their shared ever-present, the difference being that she will have aged less than he in her time below. In other words, at no time was she seeing the future. She was just watching her colleague and much of the rest of the universe aging faster than herself. It is sometimes said that to observe an object fall toward a black hole is to watch its acceleration slow until it seems to the distant observer that it freezes at the event horizon and will remain there as if stuck on a surface for a virtual infinity of time. But that too is incorrect. As a falling astronaut approaches an event horizon, from her perspective, in her own coordinate system, she will be approaching it at near light speed as measured relative to the horizon. And while her own clock will seem to her to be ticking normally, there will only be a short time to emit or reflect light toward a distant observer before, in an instant, she reaches the horizon. For the distant observer, the speed of the falling astronaut will seem to slow. Her radiant emissions and reflections will become increasingly rare. Her image will flicker and fade. Her clock will appear to almost stop ticking, and the wavelengths of light emanating from her surfaces will have dropped below the visual spectrum well before she reaches the horizon. To be clear, observer and astronaut disagree on her rate of fall. He says she's decelerating. She says she is accelerating. They also disagree on clock speed. He says hers is slowing. She says it remains constant, while his is speeding up. But they will, in principle, agree on this. She does not stop at the horizon. She falls right through, although her clock, if the observer could continue to observe it, would appear to stop at the horizon at the moment she fell through. But there is no supposed eternal spectacle as she crosses over. She simply disappears. And this suggests a paradox that will need to be resolved. But first, let's consider a specific example, using the standard equation for determining the acceleration of the event horizon. Lowercase g is a gravitational acceleration. Uppercase g is a so-called gravitational constant, which can be more accurately described as a correlate. It's not a mysterious physical property. It's a term that correlates mass in kilograms and distance in meters, just for the purpose of calculation. R sub s is the radius of an event horizon. If our sun were to collapse into a black hole, the distance from the center of the hole to the event horizon would be calculated by this standard formula. M is the mass of the sun in kilograms, and c is the speed of light, roughly 300 million meters per second. According to theory, the radius of our sun would collapse from about 656,000 kilometers down to an infinitesimal core and an event horizon at a radius of only about 3 kilometers from the core. By this actually pre-relativistic formulation, an infalling object would be accelerating in its coordinate system at over 15 billion kilometers per second squared when it reaches the event horizon. But of course, that is without adjusting for the cosmic speed limit, c, the speed of light. A significant point here is that the limit for velocity and acceleration due to gravitation is different than that due to the application of force. And incidentally, Einstein showed that gravity is not a force, it is a geometric deformation of space-time, which would not involve a mediating particle, the so-called graviton. But mathematicians devoted to quantum theory continue to ignore him. With acceleration due to a force, the more a body is accelerated, the more massive it becomes, so it can only reach the limit c by the application of an impossible infinite force. In contrast, as Galileo demonstrated centuries ago, the pull of gravity is indifferent to the mass of a falling body, although this is actually only true if a falling body isn't massive enough to contribute significantly to the mutual relationship. And mass does not increase with gravitation. See the link below the screen on relativity for why this is. So although the speed limit c is unattainable by applying a force to something that has mass, with gravitation, the speed limit for a falling body, the speed of light, is an attainable limit. There is nothing to resist the effect of gravity from bringing a falling body to c at an event horizon. This is an important distinction in black hole physics between force and gravitation. which has been pretty much forgotten in this era of quantum physics. It means that there is, at the instant of crossing the horizon, a radical change for a falling body of mass, and the apparent paradox that needs to be explored. Until the crossover at the event horizon, the astronaut's clock has seemed to her to be ticking normally, while the observer will have, in principle, watched it slow almost to zero. But now, as she reaches the event horizon, as her velocity reaches the speed of light, her clock speed must also go immediately to the clock speed of light, which is zero, and at that moment it becomes consistent with the measure, in principle, of the observer. The experience of the astronaut is supported by this standard formula for gravitational time dilation. It shows that although observer and astronaut disagree on her velocity up to the moment she reaches the event horizon, they will have always agreed whether or not she could actually be observed on the respective readings on her clock at any specific elevation. Okay, just to confirm the astronaut's status at the event horizon, let's back up to 1 meter above. At 3/10,000ths of the observer's clock speed, the astronaut is about to go from an experience of consistent, unaffected clock speed to zero. So the seeming paradox is this. Up to the moment of reaching the event horizon, the observer reports that the astronaut undergoes a steady reduction of both velocity and clock speed. But for the astronaut, there has been a constant acceleration of velocity and no change in her own clock speed. She's been in a free fall until, suddenly, she undergoes a radical transformation in crossing the event horizon. So, how are we to understand her consistent measure of normal clock speed until it abruptly goes to zero when she would suddenly agree with the observer, if comparison were possible, that it is zero? Again, the observer has in principle been accurately observing the astronaut's clock all the way down to the horizon. At any elevation, they would both agree on her clock reading, though not on her velocity. And given the previous calculation showing her clock speed to be zero at the horizon, we can use this Lorentz transformation to prove that her velocity will necessarily be equal to c at that same moment. What I'm proposing is that at the elevation where gravity brings the velocity of a massive body to the limit c and a clock speed of zero, there is a catastrophic transformation. Mass must be completely dematerialized to be brought to that state. A phase change, much as a solid is transformed to liquid and as a liquid turns to gas at a certain temperature. In an immediate and spontaneous dissolution, mass reaches the analog of a boiling point. It is actually demassed, phase transitioned into light as a fourth state of matter, or, cosmologically, should it be considered the first original state. In any case, it would be a phase change that only intense gravitation could bring about. So a black hole is, in this interpretation, a highly pressurized crush of light or radiation or energy with no so-called singularity of near infinite mass intensity at its center. Anyway, the purely mathematical idea of a singularity is cancelled by a strictly physical expectation that mass would at some point in the original collapse of the black hole obey an exclusion principle more elemental than that which supports neutron stars, and so it would resist further concentration beyond a physically normal, highly compressed but finite core. Alternatively, in the initial collapse into a black hole, the core will undergo a phase change to light, just as mass will when the event horizon is formed. With the residual core or not, following the initial collapse, a body could only enter the event horizon as light, and whether the original core of mass would gradually be dissolved by the crush and the intense radiation of the surrounding high-energy light, with a gradual phase change and dissolve into light until there is no longer a core, is, I think, an open question. All this may seem to be a radical claim, but to consider black holes in this way, a number of abiding problems with black hole theory can be resolved. If the interior of an event horizon is a more or less uniform confinement of photon energy, there is no need to struggle with understanding a metaphysical core where density would go to infinity and gravity and pressure would be so intense that space and time would break down. The expectation of an exclusion principle for mass avoids this anyway, and the popular ideas about white holes and wormholes at the supposed core, however much fun to speculate about, are rendered as science fiction. The vertical lines in this drawing represent the increasing intensity of gravity with the standard model of black holes. A black hole in the interpretation I'm offering has a very different gravitational configuration. It may consist of a primal, finite core of mass surrounded by a relatively uniform gorge of light constrained throughout by extreme pressure and a diminishing gravitation toward the center. The intensity of gravitation is maximum at the event horizon. Pressure increases in the opposite direction, determined by a presumed but unknown exclusion principle of light. Astrophysical or relativistic jets that have been observed erupting from the poles of black holes are a phenomenon difficult to explain in the conventional understanding, with the mass energy of the whole treated as an extremely small singularity within a sphere bounded at a distance by an event horizon. What could possibly bring about an eruption of such jets from an almost infinitely solid, localized, powerful, seemingly inescapable confinement? A popular proposal suggests that the spin of a hole and its accretion disk, which consists of the mass and energy spiraling into the hole on a plane perpendicular to its poles, might provide energy for such a jet, but it has been calculated that there wouldn't be enough energy produced in that explanation to fully account for the phenomenon. In terms of the present understanding, relativistic jets look like nothing so much as bursts of released pressure from a black hole. In this graphic, pressure waves are created by overwhelming infusions of energy and mass transformed to energy, arriving primarily from the accretion disk along the equator of the event horizon. A sphere of supercompressed energy can be expected to have a limit to its capacity for immediate assimilation and expansion, and so an overload could produce an eruption at the weakest points, the poles, which would result in a discharge, a jet of light from within the event horizon, joined by the excess, unassimilated plasma above the horizon, induced by a siphoning effect into the eruption stream of photons. And thus, pressure overcomes gravity. A residual core of mass from the original formation of the black hole may also be gradually dissolved under the intense compression in highly energized radiation, creating tremendous bursts of energy directed toward the path of least resistance, away from the equatorial influx from the accretion disk and toward a pole. Is it even possible that the spin of a black hole and its accretion disk, in addition to excessive pressure from within, could overwhelm the extreme gravitation at the event horizon to produce polar relativistic jets? Evidently, these spectacular jets have been observed, and a torrential release of photon pressure can provide the missing source of energy to account for them. So, having clarified some unrelativistic misconceptions about black holes, having pointed out that there is nothing to prevent massive bodies from reaching the speed of light at the event horizon of a black hole and being utterly demassed as a consequence, having offered a description of black holes that doesn't require the standard interpretation with the breakdown of our understanding of physics at a hypothetical massive singularity of infinite concentration, I've argued instead that there would be at most an original finite core of mass that would gradually dissolve into light. And having shown that this interpretation provides a satisfactory explanation of relativistic jets, I believe the model I'm proposing avoids various intractable problems, and its adoption in place of the established model is reasonable and appropriate. There is finally no need for exotic mysteries associated with the conventional black hole theories, like wormholes and white holes, closed timelines, naked singularities. There is no entropy, no holographic implications, no information loss paradox, and no firewall paradox. In describing black holes, I've used a colorful description, dark shrouds of whiteness. A more accurate and comprehensive description might be a spherical shrouded compaction of light due to extreme gravitation and compression with possibly a decomposing core of mass. Your comments are welcome. Thank you for watching and listening.